Welcome to the video on spatial positioning, okay? I'm gonna start this video by telling you this, let's summarize the whole section. This section does not matter. Why are you making a video, Jason, if the section doesn't matter? Well, what is this section? This section is spatial positioning. So when I say mathematically that this section doesn't matter, what I'm saying is spatial positioning doesn't matter. Wow, isn't that funny? Okay, so when we make a graph, right, and we have these graphs and we have like all the nodes are in a certain spot, we try to write them in a way that makes sense logically. But mathematically, it doesn't matter where we're putting brown stuff in the bowl. We could have written that node way over here and just drawn an arrow like this. Okay, when we are making graphs, the location in which we write things is just for us. It's just because we like things to be pretty. Mathematically, it does not matter at all. Okay, so, right, as an example over here, let's say that, here, I want to use a black marker. So let's say that we're making a graph and we're looking at the mileage between two different towns. Let's maybe zoom this in a little bit. All right, we're looking and we're saying, all right, we got Olympia to Tacoma. That is 31 miles. And then we've got Tacoma to Seattle along I-5. And that is about 34 miles. Okay, then we have an undirected graph here because we're looking at mileage and we don't really have any different ways of going north or south. It's pretty much the same. If we looked at times, then like at times like in the afternoon or something, this would definitely be a digraph, right? Because, you know, when you're coming back from Tacoma in the afternoon, that's going to be a lot harder than going to Tacoma from Olympia in the afternoon. I think I got my traffic things right. But yeah, so we could have this graph. Now this graph is exactly the same mathematically as this graph. Oh no, I can't do it anymore. It's too bright. It's mathematically the same as this graph. Da, 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 da. Olympia, Tacoma, 31, and all right, and then Seattle is over here, and that has a cost of 34. These are mathematically the same graph, okay? Does it look good? No. Does it make sense? Not really. But mathematically, it communicates the same exact information, okay? Very silly example of just the fact that spatial positioning does not matter for graphs. Let's take this to the next level. Okay, let's take this to the next level. Let's say we're buying some kind of game on Steam. All right, so we're gonna have 3 nodes, and let's have this first node be we do not own the game. And let's say the second node is we own the game. But it's only okay. It's one of those games that, you know, they made it, but they really just didn't put that much work into it. Because they really want you to buy the, let's say DLC actually. I don't know if people say expansion very much anymore. They really want you to buy the DLC. They put most of the good parts in the DLC. So, and let's say we can allow refunds. We can go from no game to owning a game, and maybe that costs $31. And then we can get the DLC once we own the game for $34. Sorry, $34. Okay, so this is going to be an undirected graph since we can always refund the thing and we can go from owning a game to not owning a game, no problem. Or from owning a game to DLC, or we could refund the DLC. Let's assume all of that, okay? What's the relationship between these two graphs? These two graphs are isomorphic to each other. They are both undirected undirected weighted graphs, and they have the same weights. So mathematically, these are the exact same graphs. These graphs all have the same properties. Because when we talk about connected graphs, and again, these are connected graphs, right? There's a path between any two nodes, right? There's no other node over here that we can't get to. There's a path between any pair of nodes, not necessarily an edge between any two nodes. They're not necessarily all adjacent, but they are connected. There is a path. There is a sequence of edges that connect all of these things. We're really tying a lot of the lingo together now, right? So, and yeah, when we talk about the connectedness of graphs, we talk about how we can traverse these graphs or the shortest path between these graphs. It doesn't really matter what the graph is. All that matters is its structure. And that's why isomorphic graphs are an important concept, because sometimes we can be looking at a graph and it's, if we know something about something that's isomorphic to it, then we can save ourselves a lot of time. And to say, oh yeah, let's just look, we know this about this isomorphic graph, so it holds for this graph. We could look at an equivalence class of all isomorphic graphs as well. Oh man, now we're just talking about stuff, connecting all the stuff from all the chapters. But yeah, so it's cool. But yeah, spatial positioning doesn't matter. So this graph is the same as this graph. And remember, we also have graph isomorphisms, which say that even though these two things are talking about different concepts, mathematically, they have the exact same structure. And we can bring a lot of mathematical properties from one to another. And in fact, every mathematical property will transfer from one isomorphic graph to another. Whew. All right. Now I need to pause the video and just enjoy all of this fun stuff. And you can too. Have a good one.